Welcome all to another episode of the JT University podcast. This is a re-record as the previous lecture was muted. And we're going to get into the elements of the computer system, the operating system, how programs work, and the hierarchy of computer networking, just to give you an overview. Now, when we take a look at the textbook here, I'm going to share the screen here. We're going to go over this a little bit. When we look at this, a computer breaks down to silicone chips or microchips that make up the motherboard of the computer, receives information from the input of the user or from the BIOS of the computer itself to run the operating system. These are a sequence of what are called gates. A gate is the basic logical system of a computer. Gates operate at a level that allows you to both receive a charge. Remember, as we discussed in the previous lecture, it's all a series of charge versus no charge, or negative versus positive, on versus off, 1 versus 0. This makes up binary. This makes up instructions. It makes up computer language. And we're going to take a look at how that works, both through the textbook, and we're going to take a look at how a program runs it as well when we look at logism, which is a program that's designed to simulate a computer's infrastructure. Now, give me a second as I pull up a couple of things here so that we're ready to go. All right, so I'm open this here in the background. One. Okay. Now going through this textbook here, we see this talks about the hack platform, which was a platform that was used for initial computer design in former times. It's meant to interpret machine language and simulate how a ROM and RAM works. A computer has components of a CPU, the central processing unit, which the brains of which is what we're going to discuss, the ALU. The ALU is essentially the entire computer and its functions. It's the arithmetic learning unit. In this unit, instructions are processed in 16-bit segments and are put through a series of algorithms according to a table, a registered table, that allows it to output instructions, various sets of instructions to the computer. And these are preset instructions that are designed to perform certain structures. So the hack simulates this. And later in the later chapters of this book, they actually build an ALU, which is a series. All the ALU is a series of multiplexers and gates that you're going to be triggering in order to create these compiled instructions. But at its base format, they're logic gates. And as we look at these logic gates, they form what are called Boolean instructions. This table here quantifies what a Boolean instruction or expression is. Boolean in computer terminology is yay or nay. Boolean means that something is true or is false. So a Boolean function, according to this table here, you have X, Y, and Z. Z being sort of you can call that a rogue factor. This function utilizes each of these to determine what the output will be. You have a 0 or non-charge across all three, you get a 0 output. You have 0 across the main components of X and Y, but you have a charge on Z, you get a negative output. or zero output. If you get a positive, a 1, for Y, you get a positive. If you get a positive for Y, but also Z, you get a negative. It negates it. So this would be referred to as a negator. That's something that will negate inputs to a certain extent. As you can see, when it's utilized with the X factor, a 1 here and a 1 there, you also get a 0 output. But if you have a charge to 1 or the other, X or Y, you get a positive response. If you have both, you get a positive response. This would simulate something that's called an OR gate. An OR gate requires either one or both of the positive of the gates to be charged. But if the negator isn't introduced, it negates the charge. This is how a Boolean works. Then you have tables that can show you the different factors. You can have a constant 0. You can have an AND gate, which requires both factors or all factors. It could be 4 or more to all be initiated in order for the gate to be activated. You could have an exclusive OR gate, which has to be one or the other. If it's both, there's no charge. Or the traditional OR gate, where one, the other, or both will produce a positive 1. Or an NOR, or not OR, which will be the inverse of that. Just like an NAND will be the inverse of an AND gate. And then you could have a NOT gate, which just negates whatever input that comes in. So if it's a 1, it's going to be a 0. If it's a 0, it's going to be a 1. That's a basic gate that's used often in computer chips. And we're going to see how that works a little bit later. So these gates look like this. When you see this round shape, it's universal. That's an AND gate. When you see this bullet shape, that's an OR gate. When you see this triangle, that's a NOT gate. These are the basic 3 gates that the rest are built off of. The XOR, the XAND, the NAND, and the NOR gates will be variations of these. Here's an XOR gate, similar, but just a slightly altered symbol. And once again, it's giving you the exclusive OR. So it has to be one or the other, A or B, in order to produce an output of 1. Neither or both will produce an output of 0. These are how the gates work. In HDL, or computer machine language, as it's referred to, interprets this code. It interprets a script. This is a sample script here. When you load this chip, here there's a file called xor.hdl, right? And so these are instructions, exclusive OR gate, if A or B, output 1, else output 0, and then it's closed. This is a comment that's closed in with the asterisk. So it has chip XOR, and inside the instructions, you have in, A, B. Out is out. The parts, not N equals A, out equals not A. Not N equals B, out equals not B. So this is giving not instructions for this. So these instructions will read out through the processor or the HDL program, and it'll output these set of instructions. Set A to 0, set B to 1. And this is a test script that's giving you these instructions to the program and then it's outputting them on the other end. And you have simulations for these HDL programs. I have one that I could run. We don't necessarily need to run that today. But essentially, it's parsing all of these instructions and it's implementing them into a set of commands. And this is basically what the interface would look like. You load a chip, you load the different pins and their values, and then the instructions output. You run a test script, whatever instructions you want to give it, and then you have an output file, which is a table showing almost like a legend, like we looked at earlier. So as mentioned, you have various different gates. You have the NAND gate, inputs A and B, outputs if A and B are 1, then you output 1. Output 0, I'm sorry, else you output 1. So this will be the inverse of an AND gate. So once you learn the basic 3 gates, you know how to manipulate them to see what the outputs would be for other scenarios. And we'll look at that visually in a little bit. And here you have what's called a multiplexer. The multiplexer takes in those 2 input bits and then has a selector bit. The selector is manipulated to be either a 0 or 1 by you. That'll alter what happens to the input. So then you'll have an output of either 0 or 1 based on what the selector bit is. The selector bit is activated, being that it's a 3 input gate. This can give you a 1 if you just have A, no selector. If you have nothing selected but just a selector, you'll get nothing. If you have something selected, and this has an AND function, so to speak, you have the selector bit activated and you have B activated, you get a 1. But you notice here, if you have the selector activated and A activated, you get 0. So the selector bits correspond inversely. If everything's activated, you get a 1. So this is actually rather fascinating in itself. And then you have a demultiplexer, which once again, this is inverting these instructions. So a lot of these are taking initial instructions and making modifications over time. And these can be varying bits. The way you have your IP address is 192.168.1 for most people's routers, right? That's 3 segments of 8 bits. Those 8 bits are binary. 168 is, I believe, 0, 1, no, 0, 0, 1, 1. The numbers will add up essentially to either 255 down to 0. The first bit being 1, going from right to left. The second 2, the third 4. The fourth 8, 16, 32, 64, 128. Those 8 bits will create the numbers that you use to make your IP address. But essentially, it's using binary similar to how these are. You have 1s or a 0. 1 is an activated bit, 0 is a non-activated bit. So here you have a 4-way multiplexer. Rather than just having A and B, you have A through D, and you have 2 selector bits. 1 is a 1, 1 is a 0. And so your output will be based on what the selector bit is set at and which bits are activated. So this is just to give you an idea about how instructions work and how their implementation works across the operating system. If we switch over here, we can sort of get a visualization for how this works. In this program, Logism, this is a simulator of how this program works. You have selector pins, output pins. I'm going to take an output pin, put it here. I'm going to take an output pin, put it here. And I'm going to take a couple inputs, put it here. And I'm going to load this up with some wires, right? Now, come over here. As I mentioned, this is an AND gate. This is an OR gate. This is a NOT gate. So we manipulate the AND gate. We know they both need to be activated to get a 1 here. You notice that one pin's activated, nothing's happening. Activate the second pin, voila, we have 1. In this OR gate, this wants something to be activated to generate a 1. I'm going to activate that, we get ourselves a 1. If both are activated, we get a 1. If nothing is activated, we get nothing. So it doesn't matter which pin in an OR gate, as long as something is active. And in a NOT gate, it negates whatever the input is. If I select the bit on an out gate, I get nothing here. A computer essentially receives instructions that'll be multiple layers of these logic gates being utilized. 1, 0, 1. That'll give it instructions within its registry to produce some kind of a function that is set as a task in its register. And as gates are activated, as multiplexes are activated, or as counters are activated, which are incrementing bits on a gate, this allows the computer to receive certain instructions, such as time, such as running a program in certain sequences. All these different things happen because these gates cumulatively work and they actually interact with the ALU. The ALU receives multiple instructions like these from these logic gates that funnel into the ALU, go through a series of algorithmic instructions, and output a task for the computer. And that is based as how all computers, how every operating system, that's how they all work. It's about receiving instructions and performing a task based on preset instructions in a register. So now we're going to take another look here. And if we come back to let's come back here and take a look at this. This is the Open Systems Interconnection Model, known as the OSI model, the 7-layer model used in computer networking and in computers in general. This is from the Checkpoint website. This gives you a rundown. Every transmission, when you use the internet, when you transmit data to another device, it's undergoing this. At some level, it's undergoing this process. Everything is decapsulated as it goes down to the physical layer, becomes electrical charges that transmit across some kind of medium to another device, and is encapsulated, or I should say decapsulated, when it's being presented as a program on your device, and is encapsulated as it becomes bits of data fragments that are transmitted across the medium. And everything starts at the physical layer. See, the physical layer has a PDU or unit known as the symbol. Now, this transmits electricity, light, or radio waves across the medium. It could be an Ethernet cable, it could be radio waves, whatever the case may be. It transmitted at a basic raw input from one device physically to another over a physical medium. Think of your hubs and Ethernet cables. These are operating at that low level. Layer 2, you have data link. This is when you're going to have things such as MAC addresses, because you're going to have devices that are communicating across a network and are identified and are given their information in what's known as a multiplex mode in one way or another. You're in your house, you have a computer in that room and in this room, in your living room. You're all connected to your local network. At that basic level, you're all receiving in a multiplex method the data and information that you're requesting. They're being sent to you in a collision-free environment that's sending your data to you, the next person's data, differentiating each because of your MAC addresses. Your actual physical location is what your MAC address refers to. When you hear somebody ask about that, they're referring to your physical location. Sometimes those words are interchanged. So now you receive your information, your data packets in the form of what's called a payload that's sent to you at this data link layer. It's encapsulated, decapsulated, and presented. Then you have the network layer. This is a transmission of point to point, many interconnecting nodes within a network. These packets are routed based on their IP address. Now, the IP address could be an internal or an external IP address, but now you're moving between different switches beyond just a physical base level, beyond what you can touch. Now you're differentiating at a network level. This moves onward to become the transport layer, or the TCP. You're now moving on what's known as the most popular method, the internet. The internet uses TCP protocol to transmit websites across the globe, across the state, across the city. Wherever the server is transmitting these in datagrams or segments. And these packets are sent certain set bits at a time. As we discussed, computers receive bits of data in packets with headers that identify them, and then checksums that check their validity and check their integrity at the end. And these are all broken down, decapsulated, parsed, understood by the computer, and then processed. Whether you're dealing with networks or whether you're dealing with a computer processing a program, that's how it's occurring. It's receiving these data in binary packets. Moving on, you have the session layer, which is manages what it says sessions between nodes and the data that's transmitted between them for authentication, termination of connections, or reconnections. And then you have the presentation and application layer. This is where you're presenting the program as it displays on your server. So you have HTTP as a popular layer 7 or application layer protocol. That's used to display and render a website to you as the client from a server. This is presented to you in an application or visual presentation. This isn't just happening behind the scenes, but this is where you can actually see how an HTTP site will render itself. And so this goes to show you how it goes from the minuscule level to the grand level, the level we see. And then it works in reverse. You program all this stuff, you give these instructions. When it's transmitting, it's encapsulating all this information down to a bite-sized level, and it's transmitting it to its destination. And once again, we go back to how computers receive instructions, and they process them based on a registered list of instructions that they have to process. And that's how every computer works. We want to look at it further. HTML, XML, and other web programming devices, they all use some kind of programming language. Often, one program that's used very frequently is Java. JavaScript, which is closely related, and Java, they both render sets of instructions for a program that can give more versatility to a website. A website could just be HTML, where it's just opening folders and it's just displaying content, or you can have functionality to your site. That's when you implement JavaScript, which is a program. Now, at its base, it goes right back to the language of programming. The same way a computer receives instructions in that format, in machine language, it can receive it also in programming language, where you're no longer compiling, but you're now processing the instructions. So we can see an example of this when we run this program here. This is Eclipse developer environment, Java program. In here, as a base example, Java runs in classes. A class is a group of instructions or methods that are all encapsulated together to run what's called a program. You can have multiple classes that are interconnected and refer to each other that run one overarching program, or you can just have a basic class, but they'll all run through your main public class. In this case, we have a public class called start. Now, with any program, with any time you want to do something, you need reserves, you need utilities, right? You need the tools to do the job. It's no different with a computer program. In here, you have packages where this neatly packages all these instructions. Everything that's going to be done for this particular set of programs will be inside this students package. But you can disregard that because sometimes this will default. But here I've imported a utility called random. Now, why did I import that? Well, this is going to be a program that's going to generate random integers, and it's going to do something with that so you can see how instructions work. Now, I needed that tool in order to run that. So I imported java.util.random. And here in my public class, I have a reference to a method. A method is basically a small set of instructions. It's a small program within a program. This method is called generate. If you look down here at the bottom, what's called private static integer generate, that's identifying the generate method or program, the mini program, and its set of instructions. Inside this small program called generate, we have an integer we call j equal to 45, a static flat number. Then we utilize our random utility by calling a variable we name rand and generating a random instance. Now we create another integer and we call it k. This references the random and creates an integer next int somewhere between the numbers 0 and 100. The number within these parentheses is your upper limit. So now we have a third integer that we call m. We're going to name that variable m. This is the addition of our static integer and this random integer k. And this is going to be returned by our generate formula. So now we have our neatly packaged mini program, and we go up to our main program to reference it. So now we call this program in our main program, which is start. And then we set our conditions. Remember we said before, when a computer receives instructions, it receives them based on, if this happens, do this. If it doesn't happen, do that. A scenario list of different series of events or possibilities, if you will. If running this program, you get an integer that's greater than 110, we're going to have it print out big number. If it produces an integer less than 110, we're going to print out small number, right? Simple instructions. So we're going to come up here and we're going to run this and look at this console down here. And now it prints 132. Now, we run it again, small number, but it prints 138. Now, this is based on how I position this. So each time it's printing out the number. And then it's running contingency. Small number, 98. Run it again. 62, which would be small number. Small number, 65. So essentially it's giving your program, the syntax of this could have been more neatly displayed, but essentially it's taking the number and then it's making a decision based on what criteria it meets. If it's over 110, it's doing one instruction. If it's under 110, it's performing another instruction and printing out these statements. This is how programs work. They receive instructions, they parse them, and then they follow them according to a table. So this gives you a basic outline of how this stuff works. And in the next lesson, we'll go more into networking and how you can troubleshoot a network or troubleshoot any problem by tracing it back to what are the intended and desired functions of the program. And that's the core essence of being a computer tech, a network technician, any kind of technician. This is the core essence, is understanding how you go back through these layers of the OSI model or the layers of how computer logic gates work. And when you look at the base level of how these things all function, you can understand how to properly investigate and troubleshoot an issue. So we'll look at that next time in the next lecture. And this will give you the tools you need to be a dynamic tech.